I'll try, of course, because this is a very limited time. So I'll try to cover, like usually this would be a whole day thing where you have like have the slides presenting the concepts and explaining the concepts, and then you do the code along or like the exercise. But since this is a code along, so we'll do the exercise right away. But feel free to ask me either afterwards or during if we have time, if something is not clear. But I will try to explain most of the concepts as we go. So first of all, let me make sure that everyone is connected. So does everyone have access to that notebook? So the way you do that, you can, in the event details that has been sent to you, or you can just on GitHub, you can copy this URL. I don't know why the internet is slow. And then you'll find these notebooks. So I have either the code along notebook, so the empty code cells if you want to code along with me, or if you, and the filled ones if you, just for your reference, and if you get stuck and want to copy the code, but I wouldn't recommend that. So yeah, so the ones that are named code along, these are the empty ones. We'll be starting with the classification. So this one. So you can just click on that notebook, and then you'll see a small icon that says open in Colab. Yeah. It's a bit slow. I think that streaming app is really heavy. So yeah, so here this tiny icon, open in Colab. So this will bring you here. Does everyone hear now? Okay. So this is Colab is the Google version of the Jupyter notebooks. So, and the benefit of this is you can run it from the browser on Google servers, so you don't need to overload your PC, or like you don't need to like basically do anything. You just open the with your Gmail account. If you have a Gmail account, you can create those notebooks and save them to your Google Drive. And if you can also copy them to your GitHub account, you can do a lot of things. And so yeah, so now you have just a practice session opened, but if you want, you can, in file, you can save a copy in your own drive, and then it will be, the notebook will be saved in your drive folder. So that's one option. But for now, if you're just coding along here, so you hit this icon, connect, and then it will connect you to the Python 3 kernel, or so that you can start running all the code. So yeah, when you see like, and you can see real time how much RAMs and disk space you're using. And so I'm starting with classification because it's one of the most famous and easiest as well concepts. So let me first begin by asking you, like, what do you know about machine learning? Even the broader ideas, like, do you know the main classifications or the main categories of machine learning? So anyone, if anyone wants to share something. Okay, so, but this is, since this is a beginning, an intro, a complete intro, so I'll try to, of course, we won't get into the more complex ideas, but to simply put it, machine learning is, why do you want to use machine learning? So you want to infer something from your data so that you can make a prediction. So it's not just statistical learning, it's not just analyzing your data, but you want to reach the point that you can predict something on a new set of data that was never seen before, like you have never seen before, or anyone. So the whole point is to generalize your model. Basically, generalization is a keyword that's very important to keep that in mind. So when you build a machine learning model or use an existing model, your goal is to generalize the prediction. So if you train your data on some data, of course it's a smaller subset. No matter how big it is, it's still a smaller subset. And then you with that you can predict all the unseen data. So of course there's tons of applications. either in business, in our case, in health sciences as well, in medicine, it's becoming to boom a lot. So this, for example, this is a cancer classification model. So basically, I want to train the model how to, okay, I have this the data set, and I need to predict, first train and then predict from that if I have a new sample with the variables X, Y, and Z. So you can classify, is this patient have cancer or don't or doesn't have cancer. So it depends, of course. There are the machine learning for imaging, there are machine learning for, so in this case, we only have a data frame. So it's just a table with a bunch of tests or numbers, or in this case, like a lab report or something. So this data set is publicly available. It's part of scikit-learn. So the package that we use for machine learning, this is the most popular package, is a scikit-learn or sklearn. So this library, actually, you can find lots of documentation on that library. Here. So if you just type scikit-learn, you'll find all the examples and documentation needed, so you can practice on your own time. So that's a very useful resource. The other thing, so this is, you know how it is. You're all kind of familiar with Python, or have any Python experience? Yeah. So you know how in Python, even in R, you use like it's easier, of course, to use like packages instead of like doing everything from scratch. So luckily, we have all those developers and amazing people who package those libraries for us to use, because basically all the machine learning models are like existing since since the dawn of time, like since ages. They are all like basically statistical models, and people so it's just a bunch of math that people developed, and then someone lucky for us just packaged it in a way that we can use it easily. So this library, so the first thing we would need to do is to import this library, and so we can start by, if you see the first code cell here. Okay, so you can, we won't import, of course, scikit-learn or sklearn library is very huge library, so you can always import some stuff from that library. You don't have to load the whole library for faster things that you want to do. So we will do that. So we will say from sklearn. We first load the data set. So this data set comes in this library, so the cancer data set. So import from sklearn data sets. Oh, and of course, you can tab complete a lot of stuff. Import. Oh, is it make? Yeah. Oh, so I'll import the library first, and then import, zooming in. Let me see. Does that do anything? Oh, here we go. Okay. Is that better? Okay. Yeah, I did it twice. So since we're starting with a classification, so I'm importing make classification. Oop. I do a lot of typos, so I always try to tab complete. Classification. Okay, and then we also want to import the usual line. So I'll explain. Let me type this first, and then I'll explain. Import Seaborn as SNS. So what this does is imports another library, and when you import it as something, you just basically give it a shortcut so that instead you don't have to type Seaborn each and every time. So when I am using something from Seaborn library, I will just type sns dot whatever I'm trying to use. So, and also import. Oh man, this is really slow. For plotting, we will input matplotlib.py plot as plt. And then when you do enter, you're still in the same code cell. And when you do shift enter, you're running that cell. So right now we are only like we didn't run anything. And import. Come on. Pandas as pd import numpy as np. So these are the libraries that we will be needing. So I will shift enter this. And now it's a play button. So either way, like shortcuts. And I will use for plotting, I will do this. So PLT now is the plotting library. So since I gave it a nickname. So plt.style.use Seaborn. Just so that we have everything is synced between us, Seaborn. And also I will run this. So yeah, I'm sure you're familiar. So NumPy is just the numeric libraries and all that with pandas for data frames. So now I'm importing the cancer data set. So I'll go here and type from sklearn. When you tab now, it should autocomplete. Data sets. Import. Load breast cancer. Tab. And then I will save that as a variable called cancer equals load.
Put import.
Oh, sorry. Import. Now it should appear. No. Load breast. It's not tabbing. Okay. Cancer and then brackets. So let's see if that works. Oh, equals. Oh, I removed the equals. That's why. So, okay, it seems it worked. So of course, it's a good practice. If we're having a small data set, it's good practice to visualize your data. So you view your data frame and then you try to make some plots. So that's what we will do next. So here we will, so let's name a data frame, a new data frame. So now we will use the pandas to view our data set as a data frame. So I abbreviated pandas as PD. So pd.data frame should come on. And then brackets np dot. So this is just a lot of typing, so it's okay. And then I'll open the cancer. Oops, didn't mean that bracket. I mean squared bracket. And then from that, I'll see the data. Comma, cancer, target, comma, oh, I meant the comma here, and then columns, equals NP append cancer feature names. I'll explain this. I should probably have had a new line so that you can see. Feature names. And target. And then I will say view the head or the first 5 lines by default. And then shift enter. So now you can see the data frame, all the first 5 rows of your data. So here in this cancer data set, we have the mean radius of the tumor, we have a mean texture, the perimeter. So we have a bunch of stuff. And let me see, I'm gonna go, if you go to the right, you will see a column named target. So the target usually, because we want a classification model, so we need something that's coded 0, 1, so cancer, non-cancer. So we must have a column, some kind of a column that when we're training, that tells us who's cancerous and who's not, so and coded as like binary. So whenever you have, and this is also one of the things that you need to take care, whenever you have a machine learning problem, and you're deciding which model you should use, so you have to think, okay, what's my target? Do I want to, my target is binary, so it's a cancer, non-cancer thing, it's yes, no, it's or is it something that's continuous variable? So depending on your target, if you want to predict a number, so no, that can't be classification because it's a continuous scale. Then you would have to do regression or linear regression or some kind of a, but in classification, you have a binary, you have a binary variable or the target. So then you would have to use some of the classification models. So we have lots of examples. So logistic regression is one example. And here we will actually use the most famous or the most successful classification model, which is the support vector machines. So SVM models is also a type of classification, but all of these, like I said, will depend on your target. If I can see, scroll to the right. So if you can scroll to the right, you will, oh my God, what did I do? Oh, okay. Sorry about that. I know it's super slow. I think let me open the. Okay, I will open the one with the code. Sorry about that. I'm trying to close some stuff. I think maybe the internet connection or the app is. See. Yeah, I'm closing. Yeah. It's maybe the internet. Okay. Go. Maybe I'll open this. Sorry. So again, the idea of the classification. So depending on your target, I think you can see it at your end. So do you see the target zeros and ones? So if you don't see it, it means like the ones maybe later on. So you can in the head bracket, you can either increase the number, so you can head and put 20. So 20 will show you 20 rows, or you can like from the end, you can do minus X, so you can see the end of your data frame as well. So when you see that, you will see that the target column is like zeros and ones. Okay. Yeah, stuff that happens in live coding. Oop. Run. Yes. Okay. Okay, so now I'm back here. So the next thing that we want to do, like I said, is just have a quick plot and see how this data looks like. So for here, we will assume, so of course, it's a long process in data science to select your features that you want in the model. So so that you can do like have insights from correlations, previous correlations. You know that the radius is highly correlated with the cancer, and then so that's called feature engineering. So you pick your most valuable, or like you think that the most needed variables in order to predict the cancer. So the thing is, the key thing to remember is that you don't want to put all your variables in the model, because like that's the curse of dimensionality, or like that's a whole different topic. So you shouldn't, because this way you will overfit your model. So as if you're giving your model very specific clues about this specific data set. So if you try to apply this in a completely new data set and it doesn't find all of those parameters, it will fail to generalize. So you want to be very picky and very specific down to the features that are really, really crucial and important for your predictions. So in this case, I'll just assume that the mean radius of the tumor and the mean concavity, like how it's concave, the shape is a concave or convex. So I will assume that these two features or variables are the most important for determining whether this tumor is cancerous or benign. So I'll view those two in a scatter plot, and then so you can just type this and shift enter, and then it will generate this plot. So usually also this is another way if you were unsure about what kind of model you should use or whether your model will be successful or not, you just plot it and see how it looks. So now in this code, we told it that we want to color it by the target. So remember the target is a cancer or benign, zeros and ones. So the zeros here are the cancerous ones and the one are the non-cancerous. So when we color it that way and we do the scatter plot between our two features that we think are the most important, and then we see if we see that the cancerous and non-cancerous data points are well separated, this means that it's a very nice classification problem. And so the better the data is separated, the more successful you can that more easier, not necessarily successful because that depends on a bunch of other things, but it means that you can use some kind of classifier. So a classifier, usually even with the continuous data, it's just you try to draw a line, some kind of a line that separates your classes and say, so that line, so draw that line. So if we just try to visualize it in this case, the imaginary line would be like here. Somehow, but the thing is about the different classification models is that you can do this, you can do that. Like there are multiple infinite like lines that can classify this data set well enough, but not necessarily generalized to other models. So here comes the advantage of like the support vector machine classifier. So the SVM models are very useful because they take support vectors. So they take specific data points to build. I have here a slide here. I can drag it this way. So here how it should look like. So here's the support vector machines, and we're trying to draw the line that best. So it calculates the distances between the points, these vector points and the line, and then uses all a bunch of equations. But the idea is just to support, not just draw some line that can fit, but you would have it fixed in a way that all those support vectors machine points are in equal distances. So we will view this. We will try to do this. So this is various. Let me go to the previous slides. So in this example, you will see that this line can classify it. This line can classify it. There are some. So if this is a new data that wasn't there before, it wouldn't correctly. So if this point is not there, and then I said, oh, this is the line that classifies it well, and then a new data set came and there was a point right here, it will misclassify it. So that's the idea of the support vector machines. It tries to minimize finds the ultimate distances between those vector points. And so for us to do that here in our notebook, we will so we'll again use the sklearn library. So this time we will import just the support vector classifier. So from sklearn.svm import the support vector classifier, and then I will save that just for ease, like because we don't like capital case. So we'll save that as svm instead of typing all this function every time. So we'll save it as a variable. So svm equals the support vector classifier, and we're using a linear kernel. So the kernel gives you, so there, of course, like I was explaining on lines that can classify our data, but we can get into even more complex stuff that there's nonlinear relationship, but like you can view all these examples on the documentation, that's the scikit-learn. So you can find that, okay, my class is actually like, there are a bunch of data points in the middle, and then it's surrounded by other data points. So there are tons of nonlinear problems, but here we're just using the linear classifier. So I will run this and this. And then the most important thing that you would want to do with any machine learning model is to split. Want to use your whole data set on training, because like I said, you wouldn't be able to tell if it will generalize to other data sets. And you won't necessarily have an access to a different data set at that time. So it's a good idea, a good practice that you split your data into a training set and a test set. There are tons of ways of validation that you can split the data. So there are like holdout validation, there are k-fold cross-validation. So there are multiple ways, but here simply, the simplest one of them, you just like split it. And since you want more into the training, so usually a 70-30% or 80-20% is used, depending on your size, the size of the data. But you need to make sure that the test data set is like longer, like statistically it should be at least like more than 16, but but of course you need the more the data you have, the better generalizability. So here, luckily, of course, this library has already a classifier, so we can either do it manually or we can just import. So from sklearn model selection, import the train test split. And then we will use that function to split. So here I'm naming, since I saved my data frame as df, so the new names, this is just, you can name it as much as anything that you want. So here the data frame train and then the data frame test. These are the names that you can give. And then this is equal to the function that's train test split. And then between brackets is the main data frame that I saved earlier, so the df. And then the test size. So here you can decide the proportion. So here I'm saying 0.2. It means that the test set will be 20% of my data and the training set will be 80% of my data. And then the random state, this is just like to have the same seed or like the same thing that you would. So I will run this. Oh, I didn't run this. Okay, so if it didn't give you any error, it means it ran, and then we will also show it in the next code. So as long as there are no errors, it should work. So, but to verify, I can print. So I will print the size of our training is x. So this function, the dot shape, is one of the functions. It just gives you the shape of your data. So how many rows and how many columns, basically. So when I use, and this is just a string that I want to print. So I will print the strings. Okay, tell me the size of the training set is, and then put the shape of that, the splitted data, and then the test set. So here, when you shift enter, you will see that now I have 455 rows allocated to the training set, and then 114 rows or or subjects are allocated in the test set. And we have the same number of the columns. It's also a good idea. Sometimes you would want to separate, so delete your target column so that the model won't cheat, or if you forgot. So we have the 31st column is our target, the zeros and ones. So you would want, sometimes you would just for ease, you remove that column from your test set so that you, like, the test set is completely, you don't know whether this patient is cancerous or not. So it will resemble a completely new incoming data. But for here, we're just exclude that column anyway, so you don't need to do that now. So how we will do that? So first, we will use our training set to train the model. So since we saved the support vector classifier at SVM, so we will type svm.fit and then df our train. So here we're not using the whole data set, we're using just the training set. So the df that I named as df train. And then I will use the two features that I just viewed that I saw that is classifying the cancer cells very well. So I'm using the mean radius of the cancer tumor and then the mean concavity. And then the target, I need also to specify the target, which is the target column that basically says cancer, non-cancer. So now you're training, so you need to give it the answer. And then you run this. it will show you the so it will show you, so as long as it shows this, it means it worked. So it will show you all the like parameters that are used. If you need to, of course, modify any of that, you can always tailor anything that you want. And then now we would want to inspect those the properties of this model. So now we have the model trained. And then we want to see the coefficients. You know, when you do any regression, logistic or linear or whatever, you get the beta coefficient, the effect size, and the intercept and all those. So I want to view my coefficients. So I will just print. So it already has this function saved. So the SVM, I'm telling it, please print for me the intercept and please print for me the coefficient. So basically just type those intercept and coefficient. And so, okay, so now we know it worked. It gave us all the coefficients. And then based on like all those equations, of course, if you want to go through the details later. And then the next thing I want to do is evaluate the model. So to evaluate the model here, there are multiple ways, but the way to evaluate here, I will create new variables, and then I will like try to visualize it on a plot. So just type along this code, and I will explain later. You will see later how that happens. So basically what we're doing here is we're plugging in the numbers that we got, all the coefficients here, into this equation so that we can evaluate the model on a plot. So we're just like simply writing the equation. So we can run this. And then so we ran the equation. Now we have the equation, and we need to plot it and see the line ourselves. Of course, this is a luxury that not everyone would have. Not every time you can actually view your data. Sometimes it's like millions of data points that you can't see. So you can just evaluate your model from the coefficients and all those stats. But here I'll just since we're still learning, so I'll draw a figure, and I will put both variables on the axes, and then I will use scatter plots as well, and then I will specify that my x is the mean radius, just like before, and then the y is the mean concavity, and the data is our training data set, and then the hue is the coloring. So and it's a usual thing in plotting. So the hue is a color. So the orange and the blue is colored by the target. And you can specify the palette. Like if you want to use different colors, you can Google, of course, all the libraries. So there are tons of palettes and like different customizations that you can do. And then I'll just plot the K is our and then line, and then I will label this the trained SVM model on the training data set. And you can see that the model decided that this line here is the best fitting line or the best classifier. So everyone is following along at this point? I didn't check with you, everyone. Everyone doing okay? Is there anything that's not clear? Okay, so we now visualized it. So another cool visualization thing is to view the support vectors that I showed you in the other slide. So if you want to see the boundaries, of course, we want the boundaries to be as wide as possible. We need, if your data is really classified, like really separate, the boundaries will be greater. But if you have smaller data points or confused, it will have a different boundaries. So this code is just to show on your plot, to show the boundaries, the points. And then the next plot is you draw the lines, the support vector, the decision lines. So here the ones in red are the support vectors. So these are the points that were used to calculate the distance between the line and the best line and each of the support vectors. And then I can just skip this. And then this is just visualization. It's not really important, but it's nice proof of concept. So, and this you see the boundaries. So these are all these points that were used by the model as the support vectors. And now the important thing, now we have trained our data, so we need to test it in a new data set that the model has not seen before. So we did this by, since we held out a subset of our data set and called it the train, DF train. So we'll use that data set as the training, the test set. So what we will do now, since we have our model, so we need to predict. So using the mean radius and the concavity values in the test set, how would you predict whether this person have a cancer is a cancer or benign tumor? So the way we do that is we say y predict. We save this. Of course, you can name this. So I'm naming him predict the DF test. So the test data set. And I want to use these two since I have, like I said, you can specify all your variables, but here I'm just using these two variables. So I'm specifying that use the values in the mean radius and the mean concavity columns, and then predict for me whether this person or each subject has a cancer or has a benign tumor. Is everyone here at this point? Okay. And then after this, computing the classification metrics. So now we have predicted. Of course, it's somewhere saved here. I'm not viewing it yet. But one way is to evaluate in the classifier model is to do the classification metrics. So a famous one is that simply how much of your data set was predicted as true positives, true negatives, false positives, false negatives. So this report is classification report and confusion matrix. So I will import also those two functions from sklearn. And then this is just a markdown, so just to illustrate. So I will here. I will apply, so that I will call it the confusion matrix, and then the NumPy array is the confusion matrix, and the data frame is our test data set, and then the target is the answer, because we have the target column, that's the answer, if it's correct or not. So it will compare it to the original target column, and then compare that with the y predict that I had done earlier in the model. If you remember, I did y predict, so predict for me from only those two columns whether the cells are cancerous or not. And then now I'm giving it the answer and telling, okay, compare how many were right, how many were wrong, classified as true positives, true negatives, false positive, false negatives. And the labels of the y predict is 0 and 1. And then the confusion matrix, so I will print out the data frame that says the, so here I'm just basically building this table. So I'm using the pandas to do the data frame, and then telling it, okay, index the is cancer, is healthy, and then in the columns, predicted cancer, predicted healthy. So here, this is the result. So here in how well my model performed, you can see that it predicted 66 of the 114 subjects. It predicted them as cancerous. So this is the true negatives. Sorry, non-cancerous. So these were the true negatives. Is cancer predicted cancer? So this is the true positives. So it was cancer, and then it predicted cancer. And here it was healthy, but it predicted it as cancer. So these are the false negatives. And then, false positives. And then the predicted healthy, here is 0 and was cancerous. So it did very well in predicting the healthy ones. So all the 40 So these 41 were healthy and predicted as healthy, and no data point was predicted. A healthy data point was predicted as cancerous. So you can see that it did better in classifying the healthy ones than the cancer ones, because it classified 8 of them as cancerous. But it's still a pretty good model. So we can print this report by printing this classification report as from our data frame target predict. So this will calculate the precision. So the report basically calculates the precision, the accuracy. All of these concepts are ways to evaluate your model. So the accuracy, how well, how accurate it could predict, and so we actually have exercise. I don't want to. You can do this on your own. So we have the equations here. So accuracy, you can either do it yourself or use that function. So the function, of course, brings you the report, but we have here's an exercise that you can do on your own time. So calculate for me the accuracy. So the accuracy is the true positives plus the true negatives over the true positives plus basically the total. And then the specificity is the true negatives over true negatives plus the false positives. And then the sensitivity is the true positives over the true positives plus the false negatives. So these, you don't want to have, so you have some people would hide one of the other. Okay, my model is super accurate, but actually it's not very specific because it doesn't do well with the true negatives, or it's not very sensitive, so it doesn't do well. So this also depends on how biased your data is. So usually to get the optimal accuracy, specificity, and sensitivity, you need to try to make sure as much as you can that the data is not biased. So you would have equal, for instance, 50% of your data is cancerous, 50% of your data is non-cancerous, 50 females, 50 males, whatever, anything that you think might bias the data. So try to sample it well. So sampling is one big issue that you need to take care of to avoid the bias. And of course, you have to evaluate in any model. You have to evaluate all those parameters before you can publish or predict generalize in a new data set. So, oops, I'm providing the solution. So back to our function. So we can just print this from the classification report. So we see that the precision here was very well, and the recall was very so the closer this to 1, so it's a ratio. So the closer to 1, the better. And if it's close to 0, it means that it wasn't so accurate or wasn't so precise. So this report is also a handy function that you can just give to your supervisor. Or I think we are done with classification. Not sure if we have time to go through regressions, but we had the lesson for regressions before. It's kind of similar. That's why I went specifically for the classification. But you have the notebooks over there. You can always practice. It's a simple linear regression model. It's just the way to validate, maybe lengthy, how to hold out the tests and validate your model. But this is simply how you do an SVM model. Any questions?
Is this an example of supervised learning? Because we have to compare it to some true positives and true negatives.
Yes. So this is a supervised learning. So the unsupervised would be that you don't have the label, you don't have the target, you don't have any information whether which subject had cancer or non-cancer. So the one example is that clustering. So if you don't have a label, if you don't have the answer for your training, you do something called clustering. So it basically clusters. So it plots as if you're plotting the data, and it clusters. It calculates the distance between those points. So the closer the data points are to each other, so this means that this is a cluster and this is a cluster. So if it clusters them and then you would know that, okay, I have here 2 clusters. So that means one of them is cancerous, one of them is not cancerous, and then you try to. So this is one way that people can infer from an unlabeled data, but these are we're not getting into any of those. Hopefully, in future lessons we go into those. But you will find tons of examples on sklearn as well.
And then the evaluation metric would be something different. For example,
yes.
average of distance between the clusters to
yeah.
The distance in the clusters to the distance between clusters to see how well separated the clusters are.
Exactly. So if you have all your classes overlapped, it will be a bad model because it will be confused. Is this data point closer to that cluster, or is it closer to that cluster? So, but so that depends on your data.
And if you want to, so I guess you could just add a 3rd dimension. The data was kind of overlapped.
Yeah.
If you add a 3rd dimension, you could draw a plane.
And that's called the principal component. So that's one other type. I don't know if you're in genomics. So that's one way for ancestry to evaluate. So you calculate principal components. So you keep adding an axes until like 10, 20, like we have a lot of tons. So and see which of these principal components is like, it calculates those principal components and sees which one is mostly predicting or mostly separating your data, and then you put all those PCs as like incorporate them in your model. But yeah, that's a good thinking. So that's yep.
And sorry, one last question.
No,
is this always, or basically always, or I guess it depends on the data, probabilistic? Because since you have some overlapping data, it's impossible to draw a line through it if you lacking in dimensions.
Yeah.
Components.
So yeah, these gets into a really technical question. Like we're not. This is an intro, so we're not. But yeah, you can use like Bayesian statistics. You can use like there's tons of different ways that you can modify or build your models. But these are, and also there are tons of examples that are ready-made models. You can just test them. So the way that like I see many papers published, they would just simply compare decision trees, SVMs, and whatever. So they compare all those models and they report which model performed the best, which model generalized the best. So yeah.
But like, say we had education and then we had we fed it to this model. We're like, okay,
yeah,
answer or not, and then you have to be able to have like a percentage. It'd be like,
yeah, of course.
Based on this model, we're 95% sure.
Yeah, of course.
Okay.
It gives you the percentage. Yeah. So you in the evaluation gives you how confident, how confident you are in this prediction. So it gives you all that as well. So yeah, you can play around inside Kit-learn libraries and documentation. You'll find tons of examples. And of course, you can reach out to us for any questions or any help. There we also hold some co-working sessions. You can just come with your code. If you're stuck with something, you can come to them to the co-working sessions and ask any of the. Yeah, you want to wrap up or nothing?
Sure.
Okay, thank you.